And the title of my presentation is Uncertainty-Aware Probabilistic Travel Demand Prediction using the graph neural network and the variational autoencoder for the mobility on demand services. It's quite a long title, yeah. So this is the content I will talk about in the presentation. The first one is a little information about myself, and then I will discuss the problem we will tackle in this research, and then this methodology we used, and then finally the result. The first one is about myself. My name is Peng, and I'm the second-year PhD student, working in the Smart Public Transport Lab, and at the Department of Transport and Planning, and co-supervised by the Jie and Oded. And I have a computer science background, both for the bachelor and the master. And also I work as a software engineer for a couple of years. My research interest focus on the automation, deep learning, reinforcement learning, and of course, the application and the combination with the system like that. This is about the problem, and thanks to the Oded already talked a little bit about the mobility on demand services. And so for this kind of services is a little bit different from the traditional public transport. Like they have the stops, the stations, so people can go to there and to take the train or the bus. And also the bus and the train have their schedule. And then they are heading to the specific stop or stations. And with the development of the mobility and internet, so there's another service appeared like many years ago, maybe 10 years ago. So people can request the order on their mobile with applications like to order a vehicle. So the vehicle accepts the order and come to the place the customer and pick up the rider and deliver it to the destination. So this is how it works. So there are already many successful companies in the market, like the Uber, the Bolt, Lyft, and Didi. So I think most of you are already very familiar with this kind of services already. So I think it's quite helpful, especially for the tomorrow, the scenario strike. So there's no public transport. Well, for this kind of the services, different challenges appear. First one is they should, for the operator, they should to matching the rider and the drivers efficiently with different kind of constraints like the time in the real times, because nobody wanted to waiting too long. So another one is that both the demand and the supply are quite dynamic. They keep changing across in the whole day. And this is the example like the different regions of the city. So the gap between the supply and demand keep changing. So so the operator need to manage how to allocate the resources in different regions across the city to deal with the demand. Also, the whole system, the transport system is full of different kind of uncertainty, like the weather condition, and the incident, and also maybe different kind of the event. So in this research, our task is the travel demand forecasting in this system. At the same time, we wanted to deal with the uncertainty. We wanted to quantify the uncertainty to make sure that the operator can have more information about the operations. Yeah. For the previous work, and at the beginning, most people formulate the problem as a pure time series forecasting problem. So the classical method, like the auto-regression-based method, ARIMA, was applied for this kind of problem. And then for the deep learning approach, so one is the deep AR and also the recurrent neural network and also SSTM, the approach applied for this kind of problem. And then when people are realizing that it is it's a system across the city, so they added more ingredients into the time series, like the spatial information, the latitude as the features to improve the performance of the prediction. And then people are trying to change the modeling approach of the problem. They try to model this problem as a spatial temporal problem, so they can better to capture the spatial dependencies and together with the temporal dependencies for the whole problem. And for the uncertainty quantification approach, the two approaches. The first one is the parametric, and it works like first they will give a distribution assumption, normally maybe the Gaussian, and then they transfer the prediction work from the one single value to predict the parameters, and then further construct the whole distribution. So they get a probability distribution of the for the travel demand. Another approach is the non-parametric ways, and first one is the percentile estimation. They estimate the different percentile of the demand. And another way is that they just directly to predict the lower and the upper demand of the and for the travel demand to cover the target demand in the future. So this is another way. Well, in our research, we proposed a framework we used to do this kind of work. So normally it can be divided into three modules. The first module is the spatial temporal graphing convolutional neural network, and it learned from the data, as you see in the top right. So it learned from the data and learn the features, and the features are fed into a second module, a variational autoencoder. So to compress the learned features into a latent space. And then we apply the sampling from the latent space and feed the sample latent samples into the decoder to reconstruct the further possible demand of the then we get a vector of different of the samples of the future demand potentially. Yeah. Finally, the samples are fed into a kernel density estimation, and then we can fit probability density a function for the future travel demand. So this is the whole workflow, and then we'll break it down. First step is the data process, and the original data is that is all the records of the orders. So each record they have the 10 point, and also the original and the destination. So something like also some other features that we didn't use in this research, like the price, the distance, something like that. We didn't use it in this research. And the map, first the map are divided into the different regions, yeah, by the postcode. So each region is are treated as a node in a group, so we can get a density matrix. So the edge is if they are connected in the geographic, so there's a connection. Otherwise, there's no connection. So this is not the only way. So this is the simplest way. Maybe in the future, there's a more different kind of the relationships between these regions can be explored. So then we can get this is how it is divided across the New York City. So each regions is represent the postcode area. So we can see that most of the demand are concentrated in the Manhattan area, and this is the airport. So it is quite high there. And for each region, and the trip records are aggregated into 1 hour intervals, so that our prediction time interval is 1 hour. So it is not the only way. It also can be, if you want to more shorter, maybe 50 minutes or half an hour is also possible. So this is a 1 hour aggregation here. By this way, and the data size is converted into a series of the temporal graphs. For each graph, it represents a time step in the whole series, whole time series. So then it is fed into a spatial temporal graph convolutional network, and this work is based on the previous research. I studied here. You can see it, and the first, and basically it is it has 3 blocks and stacked it together. The first one and the first 2 are spatial temporal convolution block, and for the inside structure is in the middle picture, and the first layer is the temporal convolution, and then followed by a spatial convolution layer, and then is another temporal convolution layer. And the right picture is a temporal gated convolutionary structure here. It's the 1D convolution and together with the gated linear units here. So this is how it works. And I won't go to detail of the mechanism. And if you are interested, please to refer to it. And now also welcome to discuss with it. So then the output is here is fed into the variable auto encoder decoder, because at the beginning this work is designed for the traffic flow prediction. So its output is a single value. So we want to get a probability of the distribution of the demand. We need more samples of the underlying distribution here. So the way we wanted to explore the underlying distribution is that we applied a variational autoencoder. So the functionality of this module is that it first to accept the output of the SDGCN, and it learns the feature from the data, and then it will compress the features into a latent space. And during the training phases, it will try to reconstruct the input. So after the training finished, then the latent space already it learned the features and also compressed the information about the data. And then during the prediction stage, we will try to sample from the latent space and try to feed it into the into the decoder, so that can we repeat the conduct this operation, so we get the a vector of the samples. This is what I described in the previous. So after I get many samples of the distribution, so I will feed it to the KDE, kernel density estimation. So it works like the left image. It converts the discrete values into a continuous density function here. So finally we get probability and density function at the last. So this is our objective of this research. And then for the result, and this we evaluate different metrics. There's point-based and also the interval and the probability-based metrics, and also we recorded the computation time. So the last column is our performance. So you can see that it works better for most of the scenarios, especially for the high demand area. Yeah.
Why are you using VAE? Are you using VAE to generate sample points for the prediction of?
True. Yeah. So
Can you explain what's the input to the, I mean, how the VAE is?
yeah, sure. Because for our research, it's a long parametric method, so we don't have the we don't assume the distribution of the travel demand. So there's no parameters in the prediction. So the way we wanted to get an information of the underlying distribution is that we wanted to like sampling more sample from the underlying distribution. So the method we use, we wanted to use a variational autoencoder. We wanted to generate the samples from the learned latent space. So this is the whole idea of the framework here.
Do you use the learned samples to train your model later?
You mean the learned samples trained?
Yeah. So you're generating the samples here.
Yeah.
About the possible forecasting for that.
Yeah.
Now using that, are you training your model to do the prediction?
At the training stage, after we get a vector of samples, then we computed the mean of the value, and as the predict single value and compare to the target value, and then the back propagation of the whole network. So to train the process. The way that we don't apply it to the include the KDE in the training because there's no the gradient information, so this is quite hard to train the. So this is how it works, and this is a performance of that, and then we also visualized several example locations, and the top three regions is the high demand area. So the blue line is the predicted, and the orange line is the target value. This is aligned well, I think. And also the area, the blue area, is the it is prediction interval with a confidence level of 90%. And the lower three figures is lower demand areas. So I think it works a lot better. Because I think mainly because the data sparsity. So there's a lot of zeros in these kind of areas, and also you can see from the previous demand distribution across the city. So many of the cities, many of the regions, there are quite a low demand, so the number is zero there. So this may be the reason. Now for the uncertainty quantification, we choose the three typical representative areas. The first one is the workplace region. The second is the tourism region, and the third one is the residential region. So it is two continuous days. The first one is the Sunday, and the second day is the Monday. So it's quite a representative time. And I see they are normally they are all have the higher demand during the middle of the day and also on Saturday. But at some point, especially the commuting time, the workplace and tourism and the residential, they are quite a different as maybe at the commuting time in the morning. So for the residents, it starts from the 6, but the uncertainty is quite small because it is quite a certain that most of the people are trying start working, leaving their home. But in the middle of the day, so the people have a different kind of their objectives for traveling. So it shows the different travel patterns at the different regions, and also I think is quite aligned with the real world practice here. Yeah, here is the end of the presentation. So thank you.